In this lesson, we're going to examine radical numbers. Radical numbers are those expressions which exist underneath a root sign that can't be calculated evenly. For example, root 3 is the never-ending decimal, 1.73 dot 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 dot. Okay? This thing underneath the root sign is called a radicand. Now, we like radicands that are nice numbers that come out to perfect squares, like root 4 is 2, or root 9 is 3, and so on and so on. Those things are good for us. But sometimes we're going to come across expressions that cannot be calculated evenly. So our objective today is to try to simplify these, make them easier to work with. So a couple of rules here for us. What we want to do, number one, is try to get rid of any perfect squares. If you can square root something, why wouldn't you? It's much nicer to work with. Root 9, for example. Hey, we're going to try and avoid fractions underneath root signs if we can. And we're definitely going to try and avoid fractions with root signs on the bottom. Okay, the denominator should be a whole number wherever possible. The nice thing about radicals is it can be broken into parts. For example, root 20 is the same thing as root 4, root 5, because 4 times 5 makes 20. So you can break radicals into parts. Similarly, you can break a radical that is a fraction into parts. Okay, it works the same way. So to simplify things, what we're going to try and do is we're going to try and think about the factors, not really factoring, but factors, the numbers that make up these whole things. For example, root 20 is made up of 4 times 5. Okay? We always want to try and get a perfect square and a non-perfect square, the biggest perfect square you can possibly get. So for example, root 20 could break into root 10 and root 2, but neither of those are perfect. It could break into root 20 and root 1, but there's no point because you're back at 20 again. Okay? Our objective is to think of things that are perfect, like root 4 and root 5, not perfect, so this is your perfect one, that can be evaluated. I know the square root of 4 is just 2, and the square root of 5 I can't really do anything with, so I'm going to call this 2 root 5. That's the kind of answer we're looking for. Okay, a perfect part and a non-perfect part. So some things you might want to write down somewhere on your page, all the perfect squares. Things we can think about that break into nice whole numbers when you square root them. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. We're not going to deal with ones that are a whole lot bigger probably. You may come across the occasional 12. Maybe you come across something like 400, that's a nice one. Maybe root 625, that's a nice one. Things that are nice numbers are ones we're going to come across. This is an introduction to radicals. Okay. So remember, our objective here again is we want a perfect part and a non-perfect part. Try and figure out the biggest perfect part possible. So let's try some. Root 75. What perfect square goes into root 75? I'm hoping that's a nice easy one to think about. Root 25 and root 3. This piece is perfect, this piece is not. But with a perfect part, I can actually calculate that. The square root of 25 is 5. So I end up with 5 root 3. Okay, let's try the next one. Root 8. What can I break that into? What's a perfect number that goes into 8? Well, that's a pretty easy one. Root 4. What is the square root of 4? It's 2. So 2 root 2. Okay, root 60. Now, I'm going to do this one in a weird way just for a second, okay? So I could break 60 into root 30 and root 2, but neither of those are perfect, so that's not a good choice. Okay, I could break it into, I don't know, 20 and 3, but again, neither of those are perfect, so not a good choice. Our objective is a perfect root, remember. So the only perfect root I can think of is root 4 and root 15. And root 4 is 2, so I get 2 root 15. Okay? So even though you can break it down to other numbers, make sure that one of those is perfect. And let's try root 50. Root 50, what can we go into 50? Well, that's a nice easy one. That's a 25 and a 2, which gives us 5 root 2. Root 48. Okay, again, I'm going to do this one in a weird way. I'm going to guess somebody out there said root 4 and root 12. And true, 4 does go into that. But root 12 is itself a root 4, and a root 3. And root 4 is itself just the number 2. And when you write things like this, it means multiplying. So this answer comes out to 4 root 3. Now, I said it was a weird way. If you'd been smart off the beginning, if you'd figured it out, the biggest perfect root that goes into 48 is actually 16. So you end up with 4 root 3. Okay, so what I want to point out in this example is when you think you've got the best answer, check your radicand. Can this number be broken down? Because if it can, you got to keep going. Perfect root, not perfect root. Perfect root, not perfect root. And remember, there's multiplying going on every time. Okay, so if you can, try and pick the biggest one first. That's just a little hint. Okay, so continuing on for this previous one. Root 27. Well, root 27 has a 9 and a 3. And this is all multiplying, remember. So that 3 that's hanging out the front needs to multiply with the new 3 from root 9 to give us 9 root 3. Okay, and then the last one, root 24, what goes into that? 2 and 12, but those aren't perfect. How about 4 and 6? So negative 7 times 2 times root 6 is negative 14 root 6. And that's how we can break down a radical into parts. Now we can also do operations with radicals. We kind of treat them like we do algebra. And what do I mean by that? Well, if we go back to algebra for a second, we can collect like terms. If we put these things together, we'd end up with negative x plus 6y. When we do radicals, we can think of the radical values as your variables, as your letters. Okay, so I can collect things with letters that are the same. I can collect things with radicals that are the same. I can multiply letters that are the same. I can multiply letters that are different. I can expand. I can distribute. I can do all those things. I can do them with radicals. The only trick here is that numbers go with numbers and letters go with letters when we do algebra usually, right? Same thing with radicals. So when I want to multiply things together, here's our big idea, sorry. Oh, not yet. When I want to multiply things together, I got to multiply a number with a number and a radical with a radical. How's that going to look? Well, 3 times 2 is 6. Root 5 times root 7 makes root 35. Okay. Try the next one. Root 4 times root 3, that makes negative 12. Sorry, 4 times 3 is 12. Root 6 times root 3 makes root 18. Now, here's our big idea. Make sure you've checked your final answer for can it be simplified? Can I break root 35 down? Can I break root 18 down? Because if I can't, or if I can, I should. What does 18 break into? It breaks into root 9 and root 2. So I need to simplify this. Okay. Now back to our algebra idea. So, like terms, things are the same, I can collect them. Okay. When I do collect them, only the number in front changes. My numbers change if I'm multiplying, but not if I'm adding. So if I look at this expression here, I've got two things that are the same. They can go together. What's root 3 minus root 3? Nothing. No root 3's. Okay, so what am I left with? Just 2 root 2. But try the next one. Which things can go together? I got a root 5 and a root 5. If I subtract 3 minus 4, I get negative 1 root 5. Okay, the root 7s can go as root 7s. And again, if I subtract 2 minus 3, minus 1, root 7. These cannot go together. They're not like terms. They're not multiplying with each other. They're just being added and subtracted. So stick there. Okay, so we can take this and take it to the next step. Sometimes you're going to look at radicals and notice there's nothing the same. I can't collect my like terms. So in this kind of situation, you might need to break your radicals down first. Root 20 we know can be broken down into root 4 and root 5. Root 45, root 9, root 5. Hey, they have a common root. So if I write this as a whole number, and then the root, I can now collect. I'll get 5 root 5. If we try the next one, we got to break down these roots. There's no like terms in there. We can't collect anything right off the bat. Let's see what we can do. Root 54. That's root 9, root 6. Root 24 is root 4, root 6. Root 72 is root 36 and root 2. And root 32 is root 16 and root 2. And remember, our objective is the biggest possible root in all those ones, right? I know 72 can be broken to 8 and 9, but 8 can be broken down further. So it's better to pick a 36. So we get 3 root 6 plus 2 root 6 minus 6 root 2 minus 4 root 2. Collect up our like terms now. We'll get 5 root 6 minus 10 root 2. And you can't go any further than that because the roots are not like terms and they're not able to simplify them. All right, last one of these. Oh, we can't put 50 and 32 together, obviously, so we got to break them down. So 3 root 25 root 2, 2 root 16 root 2. That gives us 3 times 5 times root 2 minus 2 times 4 times root 2, or 15 root 2 minus 8 root 2, which comes up to 7 root 2. Okay, last idea for today. So we talked about multiplying, we've talked about adding, we can put those things together. We can expand expressions, we can do FOIL, we can distribute. And we have to take the idea that when multiplying, whole numbers go with whole numbers, radicals go with radicals. If you don't see a number, you can always assume there's a 1 there, a root 1, a regular 1, whatever you need. So if I want to simplify this first thing, I want to get rid of my brackets, I'm going to multiply. This times this, and this times this. Root 3 times root 6 makes root 18.
Would Mrs. Belcamino come to the office, please?
Root 3 times 1, that's just root 3. Next, I'm going to try and break down any radicals if I can, and I can here. Root 18 is root 2 root 9, which gives me 3 root 2 minus root 3. It's simplified. I know it doesn't look a whole lot simpler, but the numbers are small. That's our objective. Let's try the next one. 3 root 2 times 2 root 6. So 3 and 2 gives us 6, and 2 and 6 gives us root 12. Try the next one. 3 times 1 gives us 3, and 2 times 10 gives us 20. I can break those down. Root 12 is root 4, root 3, and root 20 is root 4, root 5. And simplify. And simplify. And then we'll multiply. So 12 root 3 plus 6 root 5. They're not like terms, so we're all done. And last two. Give them a try. What's going on here? It kind of looks like FOIL, but involving radicals. So let's try it. 1 root 2 times 2 root 2 gives us 2 root 4. 1 times 1 is 1. Root 2 and root 3 makes root 6. Insides. 5 times 2 is 10. Root 3 root 2 makes root 6. Okay. And at the end, minus 5 root 9. Notice we still only have 4 terms, but some of those terms are made up of both radicals and whole numbers. We're going to simplify. Root 4 is like saying 2. The things in the middle, we can collect those, so minus 9 root 6. At the end, root square root of 9 is just the number 3. So we'll simplify this some more. And we can put the 4 and the 15 together, make negative 11 minus 9 root 6. That's as far as I can go. No like terms. So we're done. Okay, last one. I see a radical squared. We know that means we should write it out twice. And then we're going to do FOIL. So 3 times 3 is 9. 3 times 2 root 5 makes 6 root 5. Insides, again 6 root 5. And then lasts 4 root 25, which gives us 9 plus 12 root 5 plus 4 times 5. And we want to keep simplifying, so we're going to keep making this easier where we can. And 9 and 20 makes 29 plus 12 root 5. Okay, and there's radicals. Everything we should know about radicals. Breaking them down, working with some operations, adding, subtracting, multiplying. And we're going to be using these as we do quadratics, finding answers that are radical answers and trying to simplify them.